think we are at time. We can start. I'll just go close the door. I can go close the door and we can start.
That maybe people get a bit in, but.
We should go. We should go.
Yeah?
We should go.
Okay. So, you start.
I thank everybody. Please get settled. We are getting started soon. And Colin, if you can get the door behind you. Thank you. Thank you. Get kicked off.
Yeah. Okay. So, welcome everybody to this year's ANRW workshop. In addition, in the series of workshops we have since a couple of years. This is a joint workshop of the IRTF and ACM, and maybe as it is an IRTF event, the note well applies. So if you have any IPR to report, the IRTF chair is right in the front. Also note that we have audio and video recording. So if you're presenting or if you go to the mic, you will be recorded. Code of conduct also applies. And please note that if you participate here, go on to Meet Echo. So that should be probably the next. And no, wait a second. Yeah, you should go log into Meet Echo, and if you want to speak, go into the queue, and then go to the mic. Or if you're online, we will bring you in.
Yeah, and if you're in the room, if you join the Meet Echo, use the on-site client or light client, so you don't have to have audio and video. So we use that for queuing. And if you cannot get on, we'll be fine, like to kind of let you be in the queue, but like please make sure that it's easy for us to sequence anybody who's remote and also local. Thank you.
Yeah, the goals of the IRTF, to repeat, are to support long-term research related to network standards and protocols, and this workshop is also supportive in this area. So maybe the next. So as for this workshop, we had 61 submissions, out of which 48 were long papers and 13 were short papers. And we had a regular TPC selection process, which led to the acceptance of 20 long papers and 6 short papers. So overall 26 accepted papers, which we will experience today during the day. The sessions are mixed. They are organized according to topics, and we will end the sessions with appropriate short papers so that we have a little bit mixed flow here. Yeah, first of all, I want to thank the TPC. So here are the TPC members. It was a real pleasure to work with this TPC. It was a rare event that almost all of the TPC members did their reviews in time, actively discussed papers online, so that we had well-informed and engaged selection process, and I hope this will be reflected in the program. Online material. The papers are, at least as of yesterday evening, not yet online. This is due to a delayed process by some complications with authors. So I asked ACM when they will be able to put this online, but we had on the last minute some some issues with individual papers. So that's probably the reason why it will be delayed. We will link them on the website as soon as they are available at ACM. Yeah, again, sign on to into Meet Echo and join the queue if you want to speak.
There is one, and if not, there's a QR code in there, like right next to the mics that you can use to join in. And
the IETF program has a link. Yeah, that worked. At least I used it. Yeah. So for the agenda, so we are in the welcome already. We have a keynote which we will announce in a second. Then our first session will be about network management, and we have a break, so we are aligned with the schedule of the IETF. Then before lunch, we have the network and security and privacy session. After lunch, we will have a longer measurement session and another longer session about transport and media, and this will conclude the workshop. So as for the keynote, I'm very happy to introduce Johanna Ulrich. She is from a newly founded university here in Austria, but she will introduce this university herself because she knows better than I. Johanna Ulrich has worked extensively on internet protocols and in particular on security and privacy of the internet. So I will welcome Johanna, and so that should work automatically, right?
yeah, I'll switch the slides.
Yeah, okay, so we bring your slides up? Yeah, no problem.
Should I use this mic?
Yeah. So, it's a little bit higher. Okay.
Yes.
Just give
Hello,
me.
do you hear me? Now it's good, isn't it?
Yeah.
Well, okay. Thank you for the warm welcome. As already mentioned, my name is Johanna Ulrich.
It's not working.
Oh, still not?
I'm getting closer.
Closer? This one? No, that doesn't work.
Is it on?
It's on.
No, now it's on. now it's better? No. Okay.
It's on, yeah.
Can you hear me?
Okay. Now it's better? Well, okay. Thank you for the feedback. But maybe then we get rid of that one.
Switch the microphone off.
Okay, new start, second trial. Yeah, welcome to my session. For the introduction, now we have the next technical issue that could go wrong.
What?
I think it should work like.
Okay.
Let me take back the control.
No, but
Johanna, I'll move the slides for you.
no, now it should be on. Oh, yeah, but now it was fixed.
Okay, let me
Okay.
try to give back the control to you. Okay.
Now it
Try
should
it
be
now?
fine, yeah?
Try it now?
Okay. It's also, from my experience, the more engineers are in the room, the longer we need for the equipment. Okay, thank you. So, short introduction of myself. I worked a lot for a local research institute that's here in the city, so SPR Research, and then at University of Vienna, and now I switched to ITU Austria. Just a year ago. It's not in Vienna, it's in Linz. For those who have never heard of the city, don't worry. It's like one hour driving to the west of Vienna, and it's basically everything that's not Vienna. It's smaller, it's more industry, but still it's nice. It's nice. Why I introduced the university here, because it's kind of different from, I guess, what most of you are, let's say, used from a university. First, it's a new public university, which is very rare. That's a new one is established. It's just 3 years old. We celebrated last week, and the focus is on interdisciplinarity. So on the one hand, we only have research groups that are centered around the interdisciplinary topics, usually one is computer science and the other one is something else, so that we have still a language that we can speak about. And the second, let's say, difference is that all our students learn in projects and only in projects. And at the moment, we only have master and PhD students, but the idea is that we have groups and of students, and in these groups, there is only one, let's say, sociologist and one mathematician and one computer scientist and so on, and together they should learn. The idea is to find people who can drive digitalization and transformation in the upcoming years. But with that, enough about ITU, then there's the cliche that all we Austrians, and I'm heavily bound to these cities, we're kind of tourism directors and we advocate our city where you're already nodding your head. If you want to get rid of all the cliche stuff, go to the Central Cemetery in Austria. It's very nice there. First, because there's the graveyard of Ludwig Boltzmann, and second, it kind of combines the city kind of morbid charm with a very large cemetery. But you can also ask me offline later if you want to have any further tips. And with that, I'm already coming back to my topics. My topics are somewhere between the internet, security, measurements, and the power grid. So I basically always circle around networks, and this is also how the talk will be. I will always come back to networks, but it will circle around, and I hope you get something out of that, because that's a kind of, let's say, other way of seeing it. We start with the first part is basically that I want to focus on transitions on the internet and the fact that the internet escaped the lab. I mean, this is nothing new for us, and we always see transitions. And maybe most of you will now think about the IPv6 transition. That's more on the technological side, and I also worked on that. But I want more focus on the, let's say, how we use the internet and what comes from that. And with that, I want to go through the first part of my slides, and then the second will be about how do we measure that part of the internet and what should we focus on when we measure, before eventually coming to the power grid and why it's also relevant for the internet per se, but also not only in the common sense that we are used to think about it. Okay, so the first transition, and maybe that's the oldest one, we all know that the internet was basically a thing of the university at the beginning. So they were all, let's say, good people. And if we need to punish someone like a student that was misbehaving, we could somehow deregister their account and everything was fine. That shifted with the commercialization, and that basically everybody went on the internet. There was suddenly money involved. And as soon as there is money, there also comes somebody who wants to get this money in some way. And the problem was on the internet, I mean, there's the famous sketch that on the internet, nobody knows that you're a dog, but also nobody knows that you're kind of a bad person. And this fostered all the security testing and standards. And that's also what we see here at the IETF. I remembered when I started here reading my first standards and drafts, there was already the security consideration sections, but in most cases, what was written there was something like, this RFC doesn't consider any security, so there's nothing. Yeah, and there we have a lot involved in that way. It's just by counting that words that are written there, it seems that we focus more on security, and we also have now a process that considers security. So I would say there, it's not finished yet, but let's say that we see the issue here, and we work on it. Also, I want to remember that just word count, you can say a lot with many words or nothing with many words, or just a bit with few words, but just as a first guess or a first indicator. So, but I think the second transition is essentially one that's not that obvious for us. Usually technology, no matter whether it's the internet or the power grid or the elevator, it starts as an add-on. You don't really need it. It's a nice thing to play with, but it's not, if it's not working, it's not an issue. That was the internet in the 1990s. In the 1990s, we still wouldn't know if the internet fails, what to do. And for example, if we want to reach somebody, we could go, take just the regular phone and call. If we want to know what's going on in the world and online TV is not working, there was still broadcasting and radio and so on and so forth. Yeah. The older among us will still say, okay, we know how to do this. With the younger generation, and I also see it with my son, I explained to him the concept of radio, which was totally crazy to him, yeah? That we had to wait and go for the right frequency and all this stuff. Yeah? And in addition, I mean, training young people to use it, that might be the easier thing. The harder challenge is actually that we experience an IP convergence. So we put everything on the internet and phase out the old devices. So if we look around, who of us has still a very cable-bound old phone at home? Hands up. Well, either you all are all asleep or nobody. So barely of us. I mean, maybe somebody has an old TV, but for me, I wouldn't have a TV at home as, you know, an old TV where I could regulate broadcasting. So this means the internet is now critical also in disasters. Because when you think about what happens in disasters or crisis, the advice, at least that's what I learned back in school, you start the radio or start the TV and look for official commands or official information. If the internet is broken and all the other things are not there anymore, or I cannot use them anymore, it's just out. Yeah? And this is essentially the second side of the coin of digital convergence. Obviously, we do it because it makes things easier, it makes things cheaper, but we have the drawback in case of crisis. So, and we all seen that in the last years. I mean, there were plenty of accidents where somehow DNS was involved, and just because somewhere in the world DNS had some issues, no matter what, a lot of things didn't work anymore. I remember a time when we were sitting in the office, our internet was working fine, and with every online meeting app, you didn't know whether it works or not, or whether it has some dependencies on certain parts of the internet or not. But we also have it in events of crisis. So this is one of our measurements works. Long story short, what you see here is on the list is the different regions of Ukraine. And on the x-axis, you see the dates essentially since the start of the war in Ukraine. And you see the internet outages in the different regions. And obviously, this is an event of, let's say, extreme crisis, to put it mildly. But you see that you have outages internet outages due to these events. And this is the reason when you have to come back to all other infrastructures, or you have to maintain these infrastructures very, very well. Just one alternative infrastructure, for example, that was used just at the beginning of the war is there are still some shortwave installations not that far from here that are leftovers of the Cold War that were used during the beginning of the war to get broadcasting to Ukraine. But the luck was also that they are still there. They are not maintained anymore. So in a few years, they will also be gone. So just to indicate that we just lack this backup infrastructure, and we will even lack that, or we will lack that even more in the future. And the other coin is, this is a post-stamp from Ukraine, and you don't have to be a collector on that side, but what they started is to value the most important professions that they need during the war. And if you look at the upper left stamp, that are the people who are running the internet or repairing all the cables when they are when they are gone. Yeah. So you see, it's so important that these people are honored in their own stamp. Also, this one on the upper left, upper right, that are the people working the cellular network, which is obviously also a part of it. Good, and and this criticality was not there before, and I think it have to. And the third transition that we currently face is, or see that the internet is no longer borderless. That was also, I think maybe I'm the youngest who still know these times that we just thought the internet will bring peace and freedom to everybody, and this story unfortunately didn't work out. It was a nice story. It was somehow together with the end of history and so on, and it's just not there. There are firewalls, there are censorships, we have the power of hyperscaler, and especially for those from the European Union, they are aware of this discussion. We are currently heavily debating about getting rid of hyperscalers that are US-based, which are practically all hyperscalers, because we feel that there might be the potential to use this power against us in some way or the other. And also there are increasingly countries who try to disconnect their people from the internet. Like, for example, think about Russia, where now mobile networks are disconnected, or also Iran or Myanmar in the past. So with these three transitions, we essentially have a different internet than what was originally planned. And we also have to think about new questions on what to do with this internet. Because I guess we can agree in here that we somehow want to maintain, because it's comfortable, it makes fun, and by the way, we all would be without a job if it wouldn't be there anymore. So I guess we have a strong motivation to keep it. Here, just that's one of the measurements where we focused on the fact whether Tor is still usable in Russia, because then the censorship started quite heavily, and it seems like it's still working good, but this is just as a kind of depiction of what I just said. And this is just another fact that you see how serious the problem of digital sovereignty is within the European Union. This is Austria, and all the red dots that are communities that are currently dependent on Microsoft infrastructure. And Austria is by far not the worst within the European countries, just to get one impression. And this is now the push that we want to essentially get rid of and find a solution for that. Okay. If we feel like this is unique for the internet, actually it's not. Yeah, my second big research topic is the power grid, and we see all three challenges, problems, also there. We see on the one hand the geopolitical tensions. Just to be aware, there were some European countries who just reconnected to a totally different power grid, namely from the former Soviet power grid to European, just for being safe and being able to run this critical infrastructure. Also, this power grid somehow feels convergence. We all know that electrification is one of the major strategies to counter climate change, you know, electric cars, heat pumps, whatsoever. And this makes also the power grid even more important than before. And insofar, the trajectory is somehow comparable to the internet. And also with the digitalization that's at the moment, there comes the need for security. So it's maybe the inverse history from the timeline perspective, but you'll see all these 3 points also there. Apart from the fact that also the power grid is decentralized, meanwhile, it's really large, and both infrastructure have some ossification or experience ossification. In the power grid, you see it because the infrastructure is large and it needs a long time to build new one. but also the internet feels very shiny and changing on the upper levels, but we know down there, and I feel you're more the people who are down there, they know that things change very slowly. Just think about how long it took to reach, let's say, 50% of IPv6 adoption on the internet. Yeah? So we need to monitor and guide this transition, and here that's also an aspect where we researchers come in, and we need current insights on the internet, and this is usually what we do with internet measurements. The insights, that's the main purpose, or one of the major purposes of this research, is to get information or ideas for standardization. The other thing, and I think this will become more and more important now, is policies and laws, and obviously security testing, and also creating automated security solutions. And the last one is this internet as a sensor challenge. If you think back about the picture that I've shown about Ukraine, and where is an internet outage and where not, and most of them are related to power outages. So we could use the internet as a sensor to kind of see what's going on in the world. But if we do that, we need essentially better measurements. And with that, I'm already coming to my second second part, and it's internet measurements and how we do them. And I criticize my own research work because I think it wouldn't be very nice to criticize others, but I think it's more, fundamental to the field, how we measure, because at the moment I feel we get a lot of results, but as soon as we want to act on that, they don't feel accurate enough to put them forward to policy, for example, which in turn means that we have to go back to our foundations and how we measure and what we measure, and what are the limitations and how accurate are our measurements in order to be able to forward them. In the past, I feel this was not that much important, because on the one hand, for example, let's say for standardization, I now, I do examples, they are oversimplified, but just to make the point. If we want to know whether a security feature was out of the internet or no, a rough number on, let's say, 40% use, it was sufficient, because then you say, well, could be better, could be worse, depending on what you wanted to achieve, but that was sufficient. If we now go, for example, to law, policy, and so on, they need more accurate results, especially now. We have certain laws that come into action soon and will be executed soon, that also the state authorities have potential to scan, or at least they have the power to do so, whether they will be feasible to do it and capable and desirable to do it, that they scan the internet and then they act upon it. If you now think that, at least that's what I learned, that the state has to be very, very, let's say, careful in what they are doing when, for example, fining somebody because of lacking security something, the data just needs to be more secure and not just, I believe you have this and that, I put you a fine, this might destroy the idea that we have of democracies and the right of law and so on and so forth. So if we want to play a role in that, I feel that we have to become more rigorous first. And I just want to give you a very basic concept that helped at least the people in physics some decades ago to kind of improve their measurement execution, or how they collect data. But just be aware that I'm also just starting into the direction, so I don't have the world formula or the solution. I just provide you an insight into that. So basically in science, you have the idea of induction. So you infer a general rule from observations. And the other one is deduction. So you have a general rules and draw from that rule on specific cases. So I have some examples here. So I wander around, there's the park next to it, and you likely meet swans there and say, well, this swan is white, this is white, this is white. I guess many of you know the example, then I can infer, using induction, that all swans are white. The other thing would be deduction, that there is a general rule that stated all swans are white, and I close my eyes, you say there's a swan in me, and swan in front of me, and I say, well, it must be white. No other choice. But there was a large discussion, and Karl Reinhold Popper, by the way, he's from Vienna, but it's not because he's in there, but it's a coincidence. He rejected induction as a scientific method. Yeah, he said just observation doesn't bring anything. I mean, it's a good start to observe your environment, but it's not solely applicable as a science method. Science rather advances through deduction. And with that, you can differentiate actual science, so what we hopefully are doing, from pseudoscience like, I don't know, astrology, to name something. And also, because I already recommended the Central Cemetery, his grave is, and this is a very Viennese statement, his grave is in Vienna, but at a different cemetery. If you're interested in that, let me know later. But in the end, he said, well, we have to create experiments that are not so easy that they kind of, confirm what we believe anyway, because we people are somehow structured in a way that we collect only the evidence that somehow fit our purpose. I remember my father once calling me and saying, I thought about buying this car, and have you seen that basically everybody drives this car? And, it's because he now has considered buying this type and just ran around the street sawing this car everywhere, despite it was actually a car type that was at least not that much of a thing here. So the conclusion from that is that we should do experiments, but experiments that are created in the way that they contradict or that they are so strong that if there's contradiction, we have to remove the hypothesis, yeah. But if they survive these really strong experiments, it seems like a very good hypothesis, and a very good theory to explain our world. But we always have to be aware that there might be at some point be an experiment that removes all our insights, yeah. And a good scientist also accepts that their theory might be wrong. So we also have just the temporary knowledge. And if you look to the natural sciences and at this interdisciplinary place where I'm at the moment, yeah, I feel like that physicists are a lot more thinking in that way. They have their hypothesis, they do their experiment, they revise their theory, and they are doing this basically in an endless loop till their retirement, yeah? And with that, they move forward. I feel that we do, and yeah, sorry, I'm a bit, because it's lagging. I feel that what we are doing, and I don't want to blame you, I blame myself primarily, and I hope that it somehow makes the message. It feels like we rather look for what we have as a tool to measure, because that somehow limits us. And we start with the tool, then we do the experiments, and then we do the data analysis. And I wouldn't say it's a full stop, but it feels we have very different data points, and we are not really providing them or putting them together. Yeah, and maybe that's not. So here I have some critics about that. So we rather measure what we can versus what we want. So maybe we should go a step back. And then we have some kind of rule of thumb or Pareto principle outcomes. These are examples from my own research. So we found that many routing loops, fine, but what to do about it? Is that much? Is it not much? Is there a theory behind it? What to do? How can we, base on top of this this results? And the second is also, and this is also becoming a discussion, about our major conferences, like for example IMC, repeatability and replication. So do we get the results a second time? If not I'm measuring them, but you measure them, that would be the ideal of science. But it seems like we fail, at least sometimes. Yeah? So I would argue that we have that, and I mean, it's basically, and again, I include myself, we have an engineering background, I guess most of us. Yeah? There might be some exceptions in the room, but I would still say we're most, and engineering functions that way. But if we observe the internet, it feels rather that we are coming from the methodology point more towards natural sciences, despite the fact that the internet is still, an engineered product, but we're moving more that direction. So we should also go from the methodology and from the thinking more in that direction. And as I said, again, I don't want to blame anybody, but it's because the one who started the field are the engineers who also created this infrastructure. And so we still work in this engineering mindset, which is we try to optimize, validate solutions in comparison to discover fundamental phenomena, for example. We try to meet specifications rather than finding overall theory. We want to fit this machine for that purpose in comparison to university, and so on and so forth. Yeah? This is the mindset that most of us learn at university, and I guess, and I think education is still kind of shaping our minds, and it stays there, and sometimes it sticks there till the end of our lives. Some notable negative examples are, for example, that we believe that geolocation was essentially a solved topic for a decade, and nobody dared to ask whether the results in there are really accurate. Yeah, just with this replication, start of replication at IMC, for example, you come to a conclusion, oh, the assumptions are maybe not as good as we thought. And also, for example, there was along the fairy tale of the scale-free internet, so that the connection follow a power line distribution. If you have ever seen a router and how many connections it can have, and I guess there's 100% chance in the room, you will see that this doesn't hold the physical background of the internet. And this, as I made already the case, this kind of hinders us as a discipline to go beyond policy, security testing, or doing measurements of the real life via the internet. So again, my motivation is, and this is more or less the point where I'm stuck, how to get these principles into our domain, how to kind of transfer the ideas that physics has to our discipline, as we also have a bit different environment. One drawback is, for example, while physics stays pretty the same, yeah, so the natural principles stay the same, the internet doesn't. But on the other hand, we have one advantage, and that experiments are just cheaper. If I go to my colleague in the neighbor lab, she's spending a lot more money than we, and also repeating experiments is way more challenging for her.
Johanna,
yeah.
Would you like to take questions now, or you want to wait till the end?
Maybe wait till the end. Is that okay?
Yeah, that's fine.
Okay, thank you. So, and with that, I come to the last point. Again, going away again from how we do measurements, going more into the direction of criticality, and also thinking not only because we have permanently the feeling that we have to protect the internet and its criticality, but we shouldn't forget that the internet can also be kind of the threat. I mean, yeah, we're discussing about threats to children and social media, but I'm not now on this level, but also that the internet kind of has the potential to threaten the power grid. And so these explanations are by the European power grid, because I'm European, but the American or all the other power grids are, except from some terms that might be different and some numbers, nominal values that are different, physics is the same, also on the other side of the oceans. Yeah? Anyway, we have 50 hertz as a nominal value here. And this frequency is not constant. It always shifts a bit around this nominal value. And this is an indicator whether there's balance in the power grid or not. So if the consumption gets too high, the frequency drops. And at certain thresholds, we have some emergency routines. You see a list there. You don't have to exercise them in detail. But if you go from 49 hertz, you see that essentially 10 to 15% of the loads experience a blackout. And at 47.5 hertz, all the power plants just shut down for emergency routines because the turbines would break for mechanical reasons. And what we've thought, so the idea basically came over one or two or maybe more beers, like all good research ideas, whether you can kind of destabilize the power grid just by creating a botnet and then increasing the power consumption all of a sudden. Because then the consumption is too high for what's anticipated by the power grid operators, and then hopefully we can bring the frequency down to the thresholds we have just seen before. And this was our model. Just to be aware, this was the model of the whole European power grid, so you don't have to be an expert. This is a more coarse-grained model, but for the sake of this research, it was sufficient. And what you see here essentially at the upper line is 50 hertz and 49 hertz. That was when the first blackouts come, and you see that you can reach this 49 hertz easily before the time of 30 seconds. Why 30 seconds? Well, 30 seconds, that's the fastest response that the power grid can have. So the fastest reserve, so there are always power plants in hot standby, which step in just such a case. And the fastest ones among them are reacting within 30 seconds. So if you're able to destabilize before these 30 seconds, you essentially made it because they just cannot, counter anymore. You're just faster. And this is also obvious because if you think how many moving devices do we have in IT equipment? Well, almost none. If you think about all these turbines that are in the power grid, there is some mechanical rotation and inertia behind it, so it just takes a while. And interestingly, it also is dependent on the situation in the power grid. So what you see here is basically on the left side, it's when there is minimum load in the grid. So summer day, nobody is using electricity because they are somewhere swimming on the lake. But on the right side, we have winter, everybody's at home cooking, heating, blah, blah, blah. And also the upper row is kind of classic generation, gas turbines and stuff like that. And at the lower row, you have more renewables. So with more renewables, actually, we become more volatile to these attacks because we reach the threshold earlier. So the one in the middle with the frame around it, this was the picture that we've seen on the previous slide. And if you compare, like, if there's more load, the attacker is less successful. If there's less load, it's more successful. And if there are more renewables, it's also more successful. So we have to be aware. And I'm not saying that we shouldn't do more renewables. We of course should, but we have to be aware of that. And with that also, the internet becomes more of a threat for the power grid. And if the power grid is down, I think this is even more an issue than if the internet is down. And what we calculated, coming back to the internet, how many devices you need. Just be aware the European grid spans over the whole continent. So we need these infections also here on the continent because it doesn't work if the botnet is operating in the US, because that's not important for the European power grid. But back then, we started with, let's say, 2.5 to 10 million infection. And because there are more and more IoT devices and smart heatings and cars and so on, we're now down to 1.5 million infection, somewhere within Europe, including Turkey. And this number will go down further and further. And we started with this research back 10 years ago. We always heard, like, who should do that? Who should bring our power grid down? Well, again, this situation just has changed. Yeah, if we look to Ukraine, the power grid is a target. And also, if you think about the discussion, especially in European countries, we would never send our soldiers somewhere, especially as an Austrian, we would never do that. But you know, fuzzling around with the internet remotely via cyber operation, that's easier to sell to your public. So this is a nice way to actually do a nation state attack. And by now, we were always just thinking about, you know, is there an adversary behind that wants to bring our network down? But actually, we don't even need some adversary that's on purpose wants to bring our network down. We also calculated the power consumption of Bitcoin and Ethereum. I know Ethereum changed to proof of stake, but it's just a showcase that they exceed the reference incident. So their consumption within Europe exceeds the reference incident. So the maximum number that the European power grid can sustain. Yeah, we could now say, well, for Bitcoin, but this wouldn't solve our issue because it could also be, I don't know, some computing error in, or some software error in, let's say, a car that's widely used within Europe, yeah? And if there are millions of these cars around and they are electrical and charged, and they have a software error and they stop suddenly loading in the night, altogether we have the same issue. We also had back in the time, there was, for example, a leap second error in Linux. Thankfully then, you know, data centers were not that much of a big deal than today. And they all increased the power consumption all of a sudden. If that would happen today, I think we would have the same idea. Just here, Ethereum and Bitcoin is just, you know, the example that you don't need an adversary. A random software error is enough, and we all know that random software errors will be out there now in 10 years and also in the future. So what are the consequences? Well, we have outages, blackouts in one region or more regions. From my experience, if it's just one region, it's typically okay because you can help from the other regions. If the regions become larger or all of Europe, it's really an issue. Destabilization usually takes 30 seconds, restart 2 weeks if you're lucky, and then the problem just starts, because then you have to slaughter all milk cows because they are maybe ill. You have to clean all cooling facilities, you know, in supermarkets and so on, clean all pipes for water supply. So this is an endless nightmare. And some studies from the German Bundestag even say that we're then back to post-war economic position. Yeah? So, and with that, I already said we don't need an adversary. It's also just the regular internet as we're at the moment use it could be a threat. And this could also be, again, a starting point for internet measurements to see what's out there, what could be reached to form such botnets or just to cause such disasters as I have just mentioned. So, and with that, I come to the conclusion, well, the internet is a critical infrastructure. If you were not already aware of this before, I hope you're now. The internet, you know, the internet is threatened, but also the internet threatens other infrastructures, most notably the power grid. We need more insights. This is, by the way, not only for the internet the case, interestingly also for the power grid, because we have the situation that the former monopolies typically have the insight, but all the others who should push the energy transition, they are essentially working blind in that field. Well, and we need more rigorous methodology, therefore. And I hope I roughly made time, made the time limits. Yeah. And with that, I'm happy to take questions. At least I'm already aware that there were some. That's good.
Thank you. That was a great talk. Yeah, thanks. Go ahead. Well,
Thank you for the talk. I really enjoyed both parts.
Okay,
thank you. Second one, I never heard about, so it was really enlightening. But I do have a remark on the first one. If you want to make a difference in your measurements, having the best IOC paper is just not it.
Yeah, right.
You have to write papers to values that are less prestige for engineers, because the decision makers have usually background either in law or in political sciences, and they don't understand what they do. So when I wanted to bother of wasting a good research on the less prestigious venue instead of putting it in IETF?
I fully agree with you that this is one of also the, let's say, the blockers to kind of changing something. Yeah, because we have established structures and we want to, you know, keep them because they are cozy. Thank you. Yeah.
Thank you. Curtis?
Hi, Curtis Heimerl, University of Washington. I'm curious about some of the measurement discussion. There is a really robust critique of internet measurement at hotnets this cycle, basically complaining that as computer scientists, we're very bad at measurement broadly. And the discussion there went to the idea that the internet is not a natural artifact, and the natural sciences are not the sort of lens to use on it, but instead it's a social artifact, and things like econometrics and deeper economic methods might be a better approach. I was curious what your thought would be towards these kind of social science methods rather than traditional natural science methods.
I think, and it might be not you know, not a satisfying answer. I think it's not black and white. I think we can learn from both. I think what you introduced with the social aspects, that's for sure true, because still the internet is an engineered structure, yeah. But still, I think we can learn a lot from the method and the rigorousness, and think twice about measurements from natural sciences. But this was maybe a bit hidden in my talk. It's like, for example, that the internet changes is really an issue. We could, but as I said, I don't have the conclusion. We could, for example, to go more, when you go more into the natural science direction, that we measure things that are constant over time in the internet. Whatever this is, I have no idea at the moment. Yeah, the discussion is whether can we find something. If we can't make it, obviously we fail. Yeah, I think it's not a black and white discussion. I think it needs both. Although I mean, I know that this might not be a satisfying answer, but life is complex.
Thank you, Curtis. And for the people who participate, Curtis, can you post the link to the paper onto the chat so that people can have it after the meeting, the hotnets paper? Oh, okay, cool. Thank you. Thanks.
Yeah, thank you.
Please state your name since you're not on the queue.
I'm from Shanghai Technical University. My question is regarding your first section, the reality of the internet. I think everyone agrees that that's really critical. It's critical in the sense, in the benefits that it brings to us. It's transforming our society in every way. And it's also critical I think, in the side effect that it brings to the society. Recently, we see more and more cases of government regulations to reduce the minimum age that our younger generations have access to the internet and maybe to the social network. So, in your opinion, can the internet community play a role in our fighting with this addiction, the population level, or more in particular, our young generation's addiction to the internet and to the social media? Thank you.
So the scientists in me says, well, that's mainly people, that's not my field of expertise. But obviously we have to, like with all technology, think of how we want to use it. And there, I don't know whether these bans that, for example, currently applied in Australia, and we're also discussing them, are the right choice, but I don't dare to say yes or no because I'm not the expert in that field. But for sure, we have to discuss the impact of the internet on society. My point here is more about, you know, the structure, the infrastructure, and more in the infrastructure part. But as a citizen, let's say I'm with you. Yeah.
Okay. Thank you.
Thank you. We still have a couple of minutes left for questions. If anybody has any, please come up.
So I'll do one in between. I mean, thank you very much for your comparison with the natural scientists, and in particular the physicists. One of their activities is to design and operate subtle sometimes large, sometimes expensive measurement infrastructures. And actually the internet community has a few measurement infrastructures, just to name Kairos telescope or so, but it's relatively few. There's no professional operation of this. There's no funding for this. Isn't this a race to arms to change our perspective that we have, if we have a critical infrastructure, we need a professional measurement, also measurement tools, and also means to measure. We all know that measurement is always in conflict with the hyperscalers, with the operators, and so on. So that's a tension thing.
Yeah, I think I think the problem, or the reason why we don't have it yet, because it's relatively cheap to run measurements. So let's say not that perfect, but good enough measurements with the infrastructures that we have. And in comparison to physics, what we do with our measurements, they are not worth mentioning the money in comparison to what they do. Yeah, but I agree with you that it would make sense to.
But is it really good enough? I mean, we have seen in the last 10 years or so a lot of internet measurements where some people, sometimes us, sometimes others, actually worked out that the measurements are crap. Yep. Because they are so incomplete, the infrastructure is so incomplete that the claimed observation that just does not hold.
Yeah, right, right. Yeah. And this is maybe the first thing in all this is getting the measurement method right, because then we can, if we get that one right, and you know which observation points do we have, how are the bias, knowing the bias helps us in proceeding forward. I mean, for example, just a small anecdote. I have a physics student. She just finishes her master's, and she wants to pursue a career in traditional physics. This is also why she wants to leave my group. I'm very sad about that. But she was at the beginning, she's really nice and capable person. And she was sitting here and, don't you have any error calculation here? And we, no. You just put the average, you just calculate, yeah. I feel bad when doing this. So, yeah.
Thanks, Johanna. And I would like to also make a plug for the MapRG at the IRTF. They do a lot of measurement stuff, and if you find further things, keep continually engaged with us and bring the stuff to MapRG. And Dirk would greatly appreciate that. So thank you very much for your talk. It's fantastic, and thank you very much for coming. And hope you can stay around for the day. Thank you. Thanks.
Thank you.
Yeah, we have a couple of minutes. I just want to provide a small intro to the network management session. So we have 5 papers, and they're extremely varied. So we have quite a bit of topics going from edge clouds to dynamic segment sizing to zero copy load balancing and stuff and so on. So we want to continually run through the presentations. So we have 12 minutes for the talk and 3 minutes for questions on the long papers, and then 4+2 for the short papers. So we would ask you to hold questions till the end of the presentation. And thank you very much for being cooperative and interactive. So thank you. And Jefferson, if you can come up, I'll get you started. Do you want control? You can use the...
Hello. Good
Just
morning.
give me a sec. I'm passing slide control to you.
Good morning. My name is Jefferson Campos Nobre, and I'm going to present the work entitled Unified Network Abstraction Layer via a Knowledge Graph, which is a work mainly by the master's dissertation from Felipe. So this is the summary of the presentation. We start with some motivation for this work. Then we have the related work for the concepts employed in this work, then the proposed solution. I'm going to talk more about the information model that we're proposing in this work, some results, and then I will end the presentation with the conclusions. So the heterogeneity problem is a well-known problem for a long time in considering network management data models. So regarding the IETF, the Yang is the standard modeling language for network configuration, considering the framework with netconf and resconf. And one of the issues that is known for a long time is that there is a high structural and semantic fragmentation across vendors. So in this context, a couple of years ago, there's this workshop from IAB and MOPS, which highlighted that the distinct models that are used by the different vendors hinder network automation, sorry. So talking about this heterogeneity, the question is there a challenge for having these multi-vendors using the same model? So for motivation purpose, we use a minimal case in this problem area, which is the admin status attribute. So for example, considering even this really minimal configuration, this is represented different across vendors. So in this case, you're using, as an example, Cisco, Huawei, and Juniper. And for the same attribute, they have 3 different ways to represent it. And in Cisco and Juniper, if you have an empty leaf on the model, means that the interface is administratively down. So in this example in Huawei, we have some attribute that's not using the empty as an status. So you have one concept, 3 different implementation, and this heterogeneity is repeated across hundreds of Yang modules. So it's a very well-known problem. So there is some work on regards of this problem. So for example, there are some people that are using structural conversion for Yang models to different ways to represent the information. There are other approach that use, for example, some kind of analytics and operation regarding the data models in order to have some form of unified view. And in this work, what we propose is a unified abstraction. So our approach is try to harmonize different multi-vendor implementations in order to have a unified abstraction considering semantics for the models. So we have the contributions of this work is this work has 3 main contributions. The first one is to have this kind of a semantic model capable of representing these network concepts despite the difference between the Yang models and the ways that the vendors implement this kind of models. The second contribution is to have a 3-layer knowledge graph, which is some kind of data model, information model that is used right now by different working groups and research groups in the IETF. And we want to use this model as a way to preserve the implementations from the vendors regarding the Yang models. And this abstraction can be used in order to have unified semantic queries considering the information model. So in our architecture, we have in the right side of the slide, we have this image that shows at the top the devices. So in order to have the information from the device, we use a netconf parser. So after that, information is used to build a knowledge graph, and you use for that the Neo4j, which is a knowledge graph database or framework, as you wish. Then we use the Cipher, which is a query language from Neo4j in order to provide this unified network view. Considering the way that we try to abstract the information, we organize our information model considering 3 layers. So the first layer in the top, in the right side of the slide, is the semantic layer. And in this layer, we define vendor-independent concepts. So it's the upper part of the abstraction. Then in the middle part, we have the mapping, which maps these vendor-independent concepts regarding specific Yang implementations. And in the bottom of the right side of the figure, we have the operation layer, which stores the actual network values. So we have this organization for the information model because we think that this information can help to have a good abstraction about the data models, but also preserves the efficiency of this kind of a query regarding the Neo4j. So talking a little more about the semantic layer. So in this example, we are using the abstraction of a network interface, an interface type. So you can see that it's more like an ontology for you that are aware of this kind of information model. So we have the network interface, and the network interface has several features. So they have in the edge has feature, and then other nodes which represent the values that are associated with this this node. For example, the network interface has in description, has operational status, and so on and so forth. So in using this, we can represent some kind of universal concept of a network interface, and universal, as I mean to say, that is not attached to a specific implementation and with different features. So after that, we have the multi-vendor mapping layer. So in this layer, we associate the features with several nodes regarding the implementation. So for example, for admin status in this context, it's implemented as a netconf query for this kind of implementation. So as you can see, we are not using at this time, but it's possible to have different ways to collect the information from the network devices. It's not only for netconf, but in the course of this work, we're using just netconf for that. So we preserve, using this mapping, the abstraction that I showed in the last slide, but we can use different ways in order to feed this abstraction. And the operation layer is the layer that stores the operational status of this of the network and of the devices in the network. So this reflects what the operational and configuration behavior, which is captured via netconf. I think that one thing that I can also say that in this work we are just considering configuration, but as we see that it's possible to use this for different network management tasks in future. So let's see what the future holds for the work, but it's possible to have that. So in this context, I'm showing in the right side of the slide a more, how can I say, holistic view of the layers, considering all the layers that build the information model. So we implement, as I said before, we implemented that using Neo4j. So you can see on the top of the right side of the slide, the Cypher query, and Cypher is the, as I mentioned before, is the query language which is used in Neo4j. So we have this query, and using this query, we can have information from 3 different implementations, and in this context, it's Cisco, Huawei, and Juniper. And we can provide a unified result considering, in this context, as a proof of concept, the admin status of the interface. So what we can see in this result, and it's a proof of concept, that it's possible to have a unified view of different, considering different vendors for some value of the device in the network. And of course, after that, we can use this information, for example, to feed models and to do other stuff regarding network management tasks. Okay, so for example, another way we try to understand the features of our proposed solution. So we can use it for resolve young paths from semantic concepts, and this can enable dynamic netconf RPC generation across multiple vendors. For example, in this context, you are looking for we are looking to resolve a young path considering, for example, the vendor Huawei. So we can have this as a cipher query in the middle part of the slide, and then the response it's in the bottom type of the slide. So we show that it's possible to do that considering our proposal. So as a summary of the results, we have a single point of inference considering our work. So the semantic layer provides that, defining a unified meaning for the data model. So we translate the data model for an information model, and we doing that, we add up the semantics for the data we collect from the devices. The second result we want to highlight is the automated discovery that's possible to do, and I show the graph that used by the query in order to solve, for example, young paths, and providing the ability for construct netconf RPC payloads. The fourth result is the unified state retrieval. So as I mentioned before, we can have a single cipher query in order to retrieve information from three different implementations regarding 3 vendors. In this case, of course, it can be different implementations for the same vendor, which is something that it's also known in the young world. So it's possible to do that regarding different configurations, different models of equipment for a specific vendor also. And the last one is the contextual semantics. So we, using this semantic layer, we can have, like raw network values gain, rich standardized contextual meaning, and other possible properties or features that want to, to unify with the data models. So the conclusions of the work, so we provide the unified semantic abstraction for heterogeneous young models. We proposed a 3-layer information model preserving vendor-specific implementations. What's more, we have a way to query these knowledge graphs using, as our implementation, the Cipher query language, but this is something that is more related to the implementation of the knowledge graph at this point, but it's something that different knowledge graphs can be used. We think that that's possible to have different ways to implement that, but in this proof of concept, we used Neo4j and Cipher query language. And the final conclusion is that we provided a proof of concept for our work regarding 3 different large vendors, Cisco, Huawei, and Juniper, and showing that it's possible to do that. And of course, we can add different vendors and different models of devices to, to have a larger evaluation in the future.
Thank you.
So the future, just to finish, the future research directions, we want to automate the ontology or the knowledge graph creation using LLMs for automatic parsing of young modules and generation of mapping layer. We want to integrate with real-time network monitoring tools. So we are trying to have, another network management task, which is monitoring, in order to see if it's possible to use our knowledge graph in an efficient way. And we also want to expand the ontology by implementing additional functions for young models targets in this work. So I think this is my last slide. So thank you.
Thank you. Yunze?
Thank you.
Go ahead.
Okay. Hello? Hey, hello, Jefferson.
Hello.
I'm Yunde from Tsinghua University. Thank you for your wonderful.
Can you speak into the mic? We cannot hear you.
Okay, sorry.
Pull out the mic.
Louder.
Oh, louder? Okay, yeah. And my first question is that since what is the cost of adding a new modular or a new vendor in your mapping layer? And is this process automated or manually and what is the most difficult part of this? And my second question is that I think that the network configuration is very broad, and what is the goal of this mapping to support all the functions, or just narrow it to some high-value use cases? Thank you.
Okay, thank you. Really nice questions. For the first question, I think is the cost, right?
Yeah.
The cost of, yeah, this is something that at the first we are not evaluating, because we know that adding up an information model usually its cost on an implementation. So we're going to do that, and it's part of Felipe's thesis to have this evaluation. The second one is
The use cases, the broad
use
the
case.
coverage.
Yeah, and also is something that we want to push further in this in the next stage of Felipe's research, is to have a broader evaluation, considering, because it's really minimal evaluation in order just to prove our concept, but it's necessary to have different properties, values from the network in order to do that. Maybe not using just for a device, but try to have the network as a whole, for example, considering Yang and NetConf. And we know that. So we want to have more properties for the network being, implemented and also evaluated, and also different vendors, because we try just a small set, but there are lots of vendors that we can use. So the thing for the next steps for Philippe's research is to have a larger evaluation, considering, like you mentioned before, the costs, and also having more complex configurations and possibly other network management tasks.
Okay, thank you very much.
Thank you.
Thank you. Thanks. Eric,
Thanks.
state your name.
Yeah, and you can hear me now. Good, thanks. So, and maybe this is the same question asked a different way, and maybe I still missed it. How much of the ingestion of the model is automated versus a master's student doing work?
Yeah. I think I forgot to answer that from the first. Okay. Yeah. At this point, it's just like a student work. So we are just trying to see if the concept is valid. So it's manually we manually ingest this information for the knowledge graph, but we have some experience right now using LLMs in order to build the knowledge graph. So we think that probably it's possible to do that, but of course we have to see it's okay in terms of the the mistakes and the errors, and how the fidelity of the knowledge graph after using some kind of like automated ingestion. So this is something that it's really it is really the point of the research, and I hope that maybe in the future we can present the results considering this part and the others that the other speaker asked about.
Good, thank you. See me.
Sorry. Thanks, Jefferson. Thank you. The line is closed. Thank you. Thanks. Done? Okay, thanks.
Thank you.
Think you want to control the slides?
Hello.
Yeah, you can take it. You can take it.
So good morning, everyone. I'm Tung Duan from Technical University of Dresden in Germany. And today I would like to present Boosted, a framework that reduces state transfer latency in edge cloud. So the topic I present today is another topic, which is about edge computing. And my framework is proposed to reduce state transfer latency in edge clouds that leverage programmable data planes while keeping the existing deployments of network functions. So this work? Okay, let me start with the motivation behind this work. So network functions are the fundamental building blocks in today's networks, and they are now increasingly deployed in edge clouds. And many real-world network functions are inherently stateful, so they rely on state to operate correctly. And yeah, so just a few examples. For example, a firewall that maintains connection information, or the traffic monitors that keeps the packet counters. So yeah, this trend is becoming even stronger with emerging workloads such as AI, where conversation context is another example of state. And in fact, they have attracted a lot of attention from networking research and standardization community for many years. So you can see here. Yeah, so the previous work also showed that they consume significant amount of memories and also contribute to many production failures. So this makes it increasingly important to efficiently manage stateful network functions. Yeah. Um, okay. So yeah, so how do we efficiently manage stateful network functions? Let's start with fault tolerance. So you see the first one here, from the left to the right side. For the fault tolerance, after a failure, a recovery instant needs the previous state to resume the operation. So the state transfer is also required for scaling. So when new instances are created, so the states is also transferred to them. And the same applies to the migration. When a new instance is moved to another server, the states move with it. Yeah. So these are just a few examples. There are many other operations also require state transfer. And so yeah, so this brings us to the next challenge, the state transfer itself. So uh, so let's take a look at how the state transfer is evolved over time. We started with virtual machine migration. Many people know that, and it's also commercialized regarding virtual machine migration. So for virtual machine migration, transferring gigabytes of memory takes seconds. So containers significantly reduce state transfer. Why? Because it transfer much less state. Because you see, it doesn't use the guest OS. That's why we can reduce a significant amount of memory. And more recently, researchers have focused on transferring only the network functions that, yeah, making the state transfer even faster. But this evolution also comes with a new challenge. So recently, we have seen many emerging use cases such as smart factories with the robot here, and also autonomous driving. These use cases have very stringent latency requirements. As a result, state transfer needs to be completed with very low latency. Yeah. So meanwhile, at the same time, the edge clouds also make the problem even more challenging. For example, here you can see, yeah, the state transfer can also involve in much more complex scenarios. For example, with a split, the network function state can be split across multiple network functions to serve the users more efficiently. Later, these instances can be merged again to, yeah, when the system situations change. So this motivates us to design a faster state transfer mechanism. Yep. So based on these observations, we identified three key requirements. First, the solution should minimize the state transfer latency to reduce the service interruption. Second, the solution should preserve conventional deployment of the stateful network function in cloud environments. Or in other words, existing cloud deployment should continue to work without changing how network functions are deployed and managed. So we make sure the practicality. Yeah. And last but not least, the solution should minimize the overhead to the network functions, making it practical for real deployments. So with this requirement in mind, let me introduce Boost State. So we start from the simple observation. The state transfer between two stateful network functions is performed over the network. So this naturally leads to our idea. So instead of relying on the end host only, we leverage programmable data planes to accelerate the state transfer. So let's look at how the conventional approaches here. So from left to right. So with the conventional approaches, they perform state transfer entirely on the CPU host. So this can preserve the existing deployment, but results in higher latency and higher overhead, right? So the next one, more recent approaches move state transfer to the programmable data planes, so which can significantly reduce state transfer latency. However, they require deploying network function on programmable devices such as SmartNICs or Tofino switches. Yeah, so this make it difficult to preserve existing deployments. Yeah, and our ideas boosted here combines the advantages of these two approaches through the hardware software co-design. So we keep the network functions running on CPU hosts, and we only use programmable data planes to accelerate the state transfer. And at the end, all the three requirements I mentioned in previous slides are satisfied. Yeah. Okay. So yeah, so this is the overview of boosted. So it consists of three simple steps. First, the programmable data plane collects and transfers the state to the destination. And when the state transfer is triggered, only the remaining state from the source network function will be transferred via the conventional software stack. Yeah, that's mean from the source network function to the destination network function. And finally, the destination network function will reconstruct the complete state by combining state from the programmable network and from the source network function. That completes the state transfer. Yeah, so let me explain the detailed design of boosted. So the key idea is to partition the network function state into header state and action state. For the header state, it contains 5 tuple information, packet header information. And the action state records processing results. For example, whether a packet should be forwarded or dropped. Yeah, and the header state is continuously collected and transferred by the programmable network when the package traverses the networks. And after that, the source network function only transfer the action state to the destination, and destination network function will reconstruct the complete state by combining the header state and the action state. Yep, that's it. And let me so let me introduce our implementation. We implement the programmable data planes using P4 on a NetRoom SmartNIC to accelerate the state transfer. And our stateful network functions run on standard server equipped with Intel Xeon processor and 128 gigabytes of memory. And to preserve the conventional deployment, we develop a portable library to extract the state at the source network function and reconstruct the state at the destination. So in addition, we also include several practical optimizations such as non-blocking state reception at the destination to further improve the efficiency. And we evaluate two representative scenarios, split and merge, as I mentioned earlier. So for split, the state is transferred from one network function to multiple network functions. And for merge scenario, multiple network functions transfer their state to one single network functions. And for each scenario, we evaluate two common operations, scaling and fault tolerance. And we break down the state transfer latency into three components: serialization, transmission, and deserialization. And let's first look at the performance of merge scenario under scaling operations. It can be observed. Boosted significantly outperforms the state-of-the-art by leveraging programmable data planes. Notably, it reduced the transmission latency by 60% compared to previous work. And the same observation yeah, can be see for phone torrent operation. So boosted also achieve much better performance compared to the state-of-the-art work. So for the conclusion, we presented in this paper boosted that leverage programmable data planes to accelerate the state transfer in edge clouds. And I would like to emphasize that boosted preserves conventional cloud deployment without changing how network functions are yeah, deployed and managed, while we can still provide the low latency state transfer. And we implement boosted using P4 on our NetRoam SmartNIC. And the results of that boosted achieve much better performance compared to prior work. For example, it includes up to 60% lower transmission latency. So by that, yeah, so this is my presentation. So I'm open to the questions from audience. Thank you very much.
Thank you. Since there's nobody in line, I had a question for you. So one of the cases you handle is failover. So were you doing some continuous state transfer to keep the failover? And if so, did you quantify the overhead for that?
Yeah, so we make sure that, yeah, because so in the paper, we mentioned two common state operations, scaling and fault tolerance. But I have to emphasize that there are many operations such as upgrading the software or the network function. This is the common behavior in software engineering and also in cloud, for the cloud infrastructure. But come back to the questions. So for the fault tolerance, the challenge is that regarding stateful network function, we have to copy the state periodically. Yeah, because we don't know when the failure can happen, right? And this is the challenge. And that's why, yeah, low latency state transfer is very important. Just imagine that in the commercial cloud products, right? There are many stateful network functions. And if we have to provide the failover mechanism, so we need to make sure state transfer is efficient. Yeah, and that's why we use programmable data planes. Yeah, because nowadays there are already many products, not only SmartNICs, Tofino switches, even for Cisco. We also have in our test bed so that we can run containers on top. Yeah, for the in-network computing. Yeah, that's why we can leverage instead of rely only on the CPU host. That's introduce a higher latency, as I mentioned, and also higher overhead. Yeah.
Perfect. Thank you. Thanks. Thanks. Go ahead. State your name because you're not on the line.
Hello, thanks for your presentation. I'm Michał from TU Eindhoven. So my question was, first, I wanted to ask maybe more about the motivation. So you said that there's more complexity in edge clouds. And I wanted to know how it compares to normal clouds. Why is it more complex to do it in edge clouds? What's the reason? And maybe second question, more technically. What I gather from this is that the NF state, you basically split it to two parts, and part of it is kept on the SmartNIC, and this is what makes it faster. Is it a good characterization, or have I missed something? I wanted to just like summarize what I understood from this. Thank you.
So first, yeah, so if I understand correctly, the question is about the complexity of edge clouds, right? Yeah. So the question is, the thing is, why it makes sense, because nowadays, for example, many applications such as AR, VR, right? Or we talk about the tactile internet. These applications require very low latency, and often there are many research work. People want to upload the task to the remote server because the server have more computing resources, right? And that for the remote communication, the latency is important, right? And then yeah, so people want to move cloud resources closer to the devices such as the robotics. Yeah, but in this sense, the edge infrastructure become highly distributed at various locations, right? It can be in shopping center, or it can be at the next to the base stations, for example, right? And that's why yeah, it makes sense to make the study in edge clouds. And the second question, sorry, I forget the second question. What is it about?
I think you should take it offline with him because I think we are done with time. Thank you. Thank you very much. Ganesh, if you can step up.
Yeah, thank you, everyone.
Yeah, I give you control of the slides.
Okay. Good morning, everyone. I'm Danesh, a PhD student at MPI Informatics, and I'm presenting on behalf of my colleagues from MPI Informatics, Nokia Bell Labs, and FU Amsterdam. I'm going to start with a very simple scenario where we have a TCP connection between a sender and receiver, sender at the left, receiver at the right, and for simplicity, I've removed the ACK packets in here. The connection is working, but there might be some cases that we have a congestion on the network. We have a bottleneck here in the middle. That bottleneck could be a little bit smarter, that we have a queue, and that queue has some kind of threshold. And if the packets are passing that threshold, they can be marked with some kind of flag. That flag will go to the receiver side, and the receiver can forward it back to the sender. And sender can decide about the congestion and react to it. But I can change this scenario a little bit to add a little bit more information to the ACK packets. And that is how many congestion flags it has seen since the last ACK that it was receiving. For example, in the top left ACK packet that you see here, it's just saying that since the last ACK I sent to you, I just saw one congestion flag. For the next one, 3, 6, 7, and 9. This is some high-level idea of the accurate ECN. It's one of the latest RFCs in the community that maybe some of the authors are sitting here. But the thing is, what we can do with this extra information that we have. We already know that for classic congestion control, we were relying on the packet loss to react to the congestion, but that was just one signal, packet loss and react to it. Now we have more information. We know to what extent the congestion happened, and the reaction can be adjusted according to that. For example, if none of the packets are having any signals, it means that there's no congestion. If all of them are having signals, it means that we have a very severe case of congestion, right? Okay. There are some protocols that are working with this accurate ECN, for example, data center TCP, but it is designed for the data center environment. So it's not TCP friendly, and the traffic cannot go to the internet. And also PROC is some kind of de facto congestion control for the L4S is also doing this using the accurate ECN. The rest of the talk is going to be about the PROC. That was the case for accurate ECN, but PROC has some more features, and just one of the features that it has is that minimum packet window is limited to 2 packets, 2 segments. This is for preserving a minimal packet pipeline and also remaining compatible with the delayed ACK that might happen in the TCP connections. But it's giving one more feature to us, that is, with more packet, we can increase the resolution of a congestion signal. If we have just one packet in the pipeline, it's either 100% congested or 0%. But if we have at least 2 of them, it means that it can be 0, 50%, 100%. Okay? But there might be some cases that we have very severe congestion, very low bandwidth. I'm showing the same experiment, but this time we have just 100 kilobits of bandwidth here. And the packet sizes are 1,500 kilobytes. This means that even for sending a single packet, we will need 120 milliseconds of time, right? And the virtual RTT in the PROG is 25 milliseconds. It doesn't matter what is that, but what matters is that in one virtual RTT, we are sending less than 1 packet. With less than 1 packet, it means that we have less granularity for the congestion, and the scalability of the PROG won't work at the very low bandwidths. PROG has some solution for this, that is dynamic segment sizing. It's not named dynamic segment sizing, but for this presentation, we will name it like that. And the idea is, instead of having 1 packet that takes 120 milliseconds, how about we have 10 packets that each one is taking 12 milliseconds? It means that we send smaller packets, but with the same rate. What PROG is doing is, for having each segment size, it's using pacing rate and the virtual RTT to to decide about the segment size that it's gonna send. But one problem will appear with this, and that is the virtual RTT is noisy. Virtual RTT is some kind of a smooth RTT that TCP is estimating, and that could be noisy in the TCP, meaning that the segment size estimation could be noisy as well. We want to change this a little bit by using some kind of dynamic segment sizing that is just relying on the pacing rate, and we remove the smooth RTT from the formula. So for packets between 100 kilobits per second to 1 megabits per second, we use segment size between 150 bytes and the full MSS. We wanted to experiment this and see the effects and do some more experiments. We have one baseline that is all the packets are 1,500 bytes. Here I'm showing the segment size in the y-axis and the pacing rate in the x-axis, and the pacings are between 100 kilobits per second to 1 megabits, as I told you in the previous slide. We can have linear segment sizing as well, and we can deviate from that, as we already know. For example, cubic is working very good in the internet, so not using linear sometimes help. Okay, so we implemented this in Prague in Linux kernel, and we tested this in our testbed. For testing, we are using several experiments. For example, single flow, which is very, very rare in the internet, but we wanted to have some kind of baseline that is in a link of very congested link of 100 to 1 megabits per second, what will happen to the single flows. We had experiments where we have multiple homogeneous flows, meaning a lot of Prague flows are competing with each other. We have cases of competing with inelastic flows. We know that there are small flows in the internet that don't react to the congestion. So we wanted to show that if Prague is competing with them, what will happen to the flows? And last but not least is multiple heterogeneous flows. This is the case that is happening every day in the internet. Prague competing with other cubic or BBR flows. But because of the time limit, I don't have time to show all the results. I will go just to the single flow and the multiple heterogeneous flow. The setup is as simple as we had before, sender and the receiver, both of them are Prague. And now we have some delay emulators on the network that are emulating the delay that we want to have as a base delay of the experiments. And we have a bottleneck in the middle, which is using dual pi square, the queuing discipline of the Prague or L4S. And we have iPerf in between, and the link is throttled to very low bandwidth, as I said, between 100 and 1 megabits per second, 100 kilobits per second. So what are the packet lenses? If we consider this plot, in the y-axis, you see the 100 to 1 megabits per second of the bottleneck, and in the x-axis, you see the base RTT that we are using by the emulator, and this is the default implementation. And it's showing, and the shade of the plot is showing the mean packet length that we have in our experiment. And it's showing that almost all the packets are around the full 1 MSS. If we use the logarithmic approach, I'm not showing all the approaches that we implemented, just the logarithmic one, we see that for 100 kilobits per second, for example, we have very small packets, and when we reach to the 1 megabits per second, the peak one, it's having bigger packets. One of the benefits we saw in this is that retransmission rate decreased a lot. I'm showing the same plot, but this time the shade is showing average retransmission. The left one is the default implementation, and the right one is the logarithmic one. And we see that around 2 times the retransmission of 20 times the retransmission of the logarithmic one is decreasing. For multiple heterogeneous flows, we repeated the same experiments. This time we have several Prague flows are competing with several cubic or BBR flows. And this plot is showing the James fairness index in the y-axis, which is between 1 divided by the number of flows and to 1. Closer to 1, the better. It's showing the fairness between the flows. And we have experiments of 5 Pragues versus 5 cubics, and also 10 Pragues versus 10 cubics. For the case, the second one, each flow almost has just 500 kilobits per second. This is showing all the experiments that we have, fixed, default, logarithmic, linear, and exponential. And we see that for the fixed one, the fairness is the minimum compared to the others. And when we use any kind of dynamic segment sizing, the fairness is increasing. The same for the BBR as well. It's very surprising to see that when 5 frogs are competing with 5 BBR V3s, the fairness is almost 1. But for the case when we have dynamic segment sizing and the bandwidth is lower, we see that the fairness is increasing. So dynamic segment sizing is some kind of helping the TCP friendliness of the prog. So to summarize, we have seen that we can have different dynamic segment sizings in prog. We showed that for single flow, it's helping to choose better segment sizes during the experiments. And we showed that for multiple heterogeneous flows, not only it's not decreasing the fairness of the flows, but also it's helping to have more fairness during the experiments. You can read more details about the other experiments that we had in the paper by scanning this QR, and also I'm available in the job market, and if you want to see my CV, you can use this a second. Okay, thanks.
Thank you very much, Danish, for going through this. And for people who are like, watch the presentation, there's a lot of backup slides too with like more information. So like, please go take a look. There's about 40 backup slides. So thank you very much. And Lars, go ahead.
Hi, Lars at Mozilla. Thanks for the talk. It was very interesting. Two sort of, I guess, clarification questions. One is your flows are bulk flows, right? Or what flows are they?
They are IPERF flows.
They are?
IPERF. It's bulk.
IPERF, so bulk, yeah. Okay. Have you looked into non-bulk traffic or application limited traffic?
For the experiment with the inelastic flows, we were using HPing to DDoS the link. That one is not using bulk traffic, but for the prog traffic, we were always using the bulk because we wanted to see the reaction and having the flow long enough to see the dynamic segment sizing is kicking in or not.
So I'm asking because I work for a browser vendor, and many of our flows are not.
It's a very good question. Yeah, it could be one of the experiments we can run.
The other question I had was, so this idea of segment slicing is really old, and it's nice to see it like reappear now. There was like a PILC document from a really long time ago, but it talked about exactly this, that you want to like have smaller size packets to increase your packet rate. Have you looked into this? Because obviously, if you send smaller packets, your header to payload ratio gets worse. And I sort of wonder if it matters here, and you've decided it's okay, or whether that's something you still want to look at.
Yes, it is adding overhead. That's not you cannot hide that. But the thing is, at least for the case that we had the very congested link, because the retransmissions were much higher for the other experiments, we saw that the overhead is some kind of is a trade-off. It's okay. Covering that retransmission. So
because you don't need to retransmit, you can justify spending a little bit more on headers.
Yes.
Okay.
And also it's helping the scalability of the prog in the cases that for a very short term, for example, we have a burst of other traffic and the prog is adjusting its segment sizing. It will help the prog to keep its scalability and get the flow back, get the enough feedbacks from the network.
Thank you.
Thank you.
Thanks, Lars. Gori?
Gori Fairhurst. I liked this piece of work. It was really good for you to bring it here. I have a question about what happens when we have tunnel encapsulations on the bottleneck. So we have tunnel headers as well as the headers. So when you scale down to 150 bytes, there's going to be an awful lot of tunnel header. Do you somehow figure this out, or do you just ignore that? I don't know what to do.
I think you mean the overhead of the header when we have a smaller packet.
I think he means tunneling. So if you have like another additional layer of tunneling, the overhead increase becomes more visible. That's Gori's point.
I think it won't impact this because it's just adding a new header. So our packets are still small enough to get enough feedback, right? If we have 10 packets, it's fine. If we have 9 packets, it's more granular than just having 1 or 2 packets.
Okay, I'll follow up later, perhaps. That was fun.
Thank you. Roland?
Roland Bliss, KIT. How long did you let the experiments run for the fairness?
I don't recall that, but I think it's more than 4 or 5 minutes. So it was long enough to see the
Yeah,
impact.
sometimes VBR takes some time to converge. If it
Yes,
converges at all, that's what
that's
I want.
correct. That's
Okay,
correct.
thank you.
We have seen that in previous research.
Yeah, but that should be sufficient, basically.
Thank you. Thanks, Roland. Thank you. Thanks, Anish. Thank you.
Take this.
Oh, no, it's the other way around.
Okay, so hello, my name is Michał. I'm a part of PhD program at TU Eindhoven, and as a part of my internship, I was doing work on moving layer 7 load balancing towards zero copy to get the performance benefits. So first, a small division, so we know what we are talking about. So layer 4 load balancers is where the clients connect to a load balancer, and connections are assigned to the servers, and they are basically pinned. Whereas with layer 7 load balancers, what happens is that you, as the clients connect, you actually can spread the requests around the servers, and that allows you to do things like content routing. It allows you to have different protocols between front end and the back end, like HTTP 2 on the front end, HTTP 1 on the back end. And both of those nowadays are encrypted. And the problem that this causes is that you have a lot of copies to do. And they are not copies of an easy kind, because a lot of headers of TLS, of HTTP are intertwined. So the normal way that this is done is between libraries, there are what we call semantic gaps. These semantic gaps makes it so that when one layer wants to ask for the data, it has to provide the data in a stream, which makes it hard to make it into a zero copy solution. But what we identify nowadays is more and more things are offloaded to the hardware. One of those things is a TLS offload, which makes it much more practical to try to achieve zero copy. Also, user space stacks have advanced throughout the years, so we can also try to use them. And what you actually can do is you can expose the data buffers to the load balancer, so it only uses pointers. It can still translate the headers, but doing it allows the data to stay where it is, because it's already received as decrypted. We implement this solution as a proof of concept in a small NGHTTPX load balancer. It's based on NGHTTP2 library. And we use XLIO, which is a user space TCP stack. It's very easy to use. It has a lot of features already built in. And to those, we implement the additional API that allows you to actually receive, as I showed before, pointers, not actually you copy the data. And as an experiment, we run this load balancer. We use just one core, but it easily scales. It's driven to full utilization, so we are testing how much cycles you are actually using effectively. We just use 10 clients. The requests are load balanced across 2 backends, 10 outstanding requests in HTTP. All experiments use XLIO, so to make the comparison fair. And we can see that the TLS offload itself only slightly improves the performance. So the cost is not really in TLS, it's in the copies. But when you actually move to the zero copy, we get at the higher file sizes, even up to twice the performance. And as a conclusion, this is a research prototype to show how important the zero copy could be. But the real load balancers, which there are many, would have to move themselves towards getting those benefits. And that's it. Thank you for your attention.
Thank you, Michal. Any questions for Michal? If not, thank you. And yeah, thank you very much. And people can talk to you offline. Thank you very much. Thanks. Now for the last presentation of the session, Anudeep.
Sorry?
We cannot point.
No?
No. The remote people cannot see it. If you
Okay.
point
Yeah,
right.
right. That's right.
Hello. Hello. Hello, everyone. I am Anudeep. I'm going to present about Pinocchio, a framework for...
Get the mic a bit closer to you.
Hello, this is fine. Yeah. I'm going to present about Pinocchio, a framework for queuing onset prediction in mobile edge networks using reservoir computing. So real-time interactive applications such as XR benefit from early queue detection. So Pinocchio predicts this near future onset of queuing. In typical congestion signals such as loss or RTT, they have their own set of drawbacks. What we do is we use queue buildup indicator, QBI, a metric, which is like the difference between estimated packet count that is sent by the server and the number of packets received at the UE. And if this parameter is greater than 0, that means that the queue is building up at the base station. And then if it is less than 0, the build-up queue is being drained. So this is our test bed. We use open-air interface here for the 5G. And we have the edge server, which timestamps the packets and send through this OAI core and base station to the UE. And the Pinocchio framework, like for the prediction, it is in the edge server. And the UE reports periodically some measurements such as QBI here. And we use a certain input features, QBI, and some derived features such as mean or variance through a certain window interval, and then train ESN echo-state network, and then use the output for the prediction framework. We train using single flow and then test using unseen TCP cubic and BBR flows. So in this figure shows the relative time from onset, like a t equals to 0 shows the time at which the queuing onset begins. We want to predict it before t equals to 0. That means at t less than 0, we would like to predict it. And the green ones here shows some information, like so there is correlation between one-way delay increases and one of the features of this QBI, and we show that okay, we have some relation which this eco-state network exploits to predict the onset of the queuing. And if you move further away from region, for example, the red ones here, there is no much information here for the ESN to exploit. So at this stage, the prediction is not easy to, or it's not possible. This is the prediction behavior that we observed. So the actual onset, like the event of queuing onset, is at shown in circles, green circles, and then the predicted what we observed through this Pinocchio framework is in red. So we are able to see we predict the onset of the queuing. We also have the F1 scores. So if you want to predict farther from like 50 milliseconds away from the event, it's okay. We can do that. And if you want to do at 100 milliseconds, like 2 horizon steps away from this, it's possible. But if it is 3, it slowly degrades. These are the conclusions. Next, we'd like to integrate this with a rate controller to see the network utilization and latency performance. Thank you.
Thank you. We have about 30 seconds for questions, if anybody has any.
Hi, this is Rüdiger Geib, Deutsche Telekom.
Can you please state your name? We cannot hear you.
Yes, hello. My name is Rüdiger Geib, Deutsche Telekom. This seems to replace L4S, or did you investigate L4S? Because I think that pretty much solved the problem. Thank you.
Sorry, I couldn't hear.
You didn't hear? I didn't hear either. Can you speak up a bit?
Yes. Your solution seems to copy the behavior of L4S, which would explicitly mark the onset of congestion and schedulers. And that is deployed already in mobile networks, at least for 5G SA. So did you investigate that, or?
Oh, so if I understand correctly, you were asking about L4S implementation or checking our framework with the L4S implementation, right?
Yeah, yes, he wants to understand the difference.
So yeah, we are also working on that. So this is the preliminary results that we obtained. Next, we would like to show the improvements or any improvements that we get from L4S or other kinds of implementations as well. It's basically in the pipeline.
Thank you. Thank you very much. And yeah, you should catch up with him offline in the break. So we have a half-an-hour break. So thank you very much for being an awesome group. Thank you.
Okay, this is time for a break now.
And we would like to thank that yesterday night.
We join in half an hour.
It's around 1 or something.
No, that's not bad. I was just reading my piano. I just want to make sure I had everything uploaded, not for now.
Yeah.
I'll be back in like 20 minutes or so.
Hello.